All right, so what we were doing yesterday was we were going over the reaction types, and we learned a couple different ones. A lot of people did very well going over the actual identifying reaction types. But what we're doing today is kind of taking a step forward. What we started doing yesterday was taking a step forward, and we were predicting products. Okay, so this is kind of tying in all together of what we've learned before, kind of from the bonding unit to the periodic table unit all the way to now. All right, so this is where if you haven't been really paying attention, you haven't been following along, then it's going to be pretty difficult because you're going to be lost because you didn't build on itself. So I'm trying to make this as a resource for those of you who want to get back on track, and hopefully we can. But some essential things that you're going to need for this chapter, for this unit, is you need a labeled periodic table. I can't stress that enough. You need a labeled periodic table because it's going to tell you the charges of things. You're going to need it for forming compounds. You're going to need your activity series, which is also in this PowerPoint. And you're going to need your polyatomic ion resource sheet. Okay, so that's all being tied together into this predicting products section. So without further ado, let's go ahead and recap a little bit of what we were doing yesterday. So with the synthesis reaction, what you got is multiple reactants coming together to form one product. All right. So what we're doing is we're trying to predict what is that product going to be. So here we're given potassium and we're given chlorine. All right. Well, if they're coming together to form one product, what do you think that product is going to contain? What two elements? Exactly, potassium and chlorine. So here's the catch, though. We know it's going to contain potassium and chlorine, but we don't know what the ratio is, all right? That's what we got to figure out. We don't know if it's K2Cl3. We don't know if it's K4Cl2, something like that. So how do we figure that out? Charges, okay? We know that KCl is an ionic compound. How do we know that? Potassium is a metal, chlorine is a nonmetal. Therefore, it's going to form an ionic compound with charges in it. So this is where you look for their charges. Potassium on the periodic table has a 1+ charge, and I'm not presenting. I'm not restarting. Oh, fine. And chlorine has a 1- charge. So the question is, what product are they going to form, and what's the ratio going to be? It's 1-to-1. So we got 1 potassium to 1 chlorine. So are we done? The answer is yes. Okay. Last period, someone asked, Mr. Cully, where'd the other chlorine go? We had 2 over here, and we only have 1 on the right side. Well, that's what you do to balance. That's what balancing is for. So really, you're going to have 2 potassium, 1 chlorine molecule, and 2 KCl's. That's how you would even it out. Okay. So that's where that chlorine essentially went. All right, let's do a similar one. This one's down below. We have N2 and we have lithium. Okay, N2 and lithium. So here what we're doing is the exact same thing. We know that they're going to form a compound with lithium and nitrogen. We don't know the ratio, so we got to figure that out. In a ionic compound, nitrogen is going to have a 3- charge. Lithium is going to have a 1+ charge. So how many lithium do I need to cancel out nitrogen? 3. So your product's going to be 3 lithium to every 1 nitrogen. Why did I write lithium first? Because it's the metal. The metal always goes first. All right. So lithium 3, nitrogen 1. Same thing down here. What we're doing is we have a metal with a nonmetal, magnesium 2+, iodine 1-. So what we're doing is we're asking ourselves, okay, what is the compound that they're going to form? Well, if you have magnesium 2+ and you have iodine 1-, you're going to need 2 iodine to cancel out magnesium's charge. So it's going to be MgI2. So we're starting to see a pattern here. With all these synthesis reactions, what we're doing is we're basically saying, okay, I've got these 2 reactants, and I'm going to take the elements from those, put them into one compound, one product, and I got to ask myself, okay, what's the formula going to be based on their charges? So that's all we're doing all the way down this line, okay? This one's a little bit more unique. We got hydrogen and we got bromine together. Hydrogen and bromine. Hydrogen and bromine are both nonmetals. But what we're going to do is we're going to still give them charges anyway because we're going to treat it like that. So hydrogen would have a 1+ charge. It's in that column. Bromine would have a 1- charge. So what compound would they create? It's going to be HBr because it's a 1-to-1 ratio. 1 hydrogen will cancel out 1 bromine.
So if it's the 2 of the same, like 2 metals and 2 nonmetals, it doesn't matter what order they're in?
2 metals, 2 nonmetals. So like, say that again.
So like that one is 2 nonmetals, so
Yep.
it doesn't matter which one goes first.
Oh, I see what you're saying. Okay. If hydrogen's included, then it's always going to be hydrogen first. You're not going to get an example where it's not going to contain hydrogen where we're doing synthesis. So hydrogen just always goes first because technically hydrogen is a metal. Maybe you've heard of metallic hydrogen before. We think of it in the scope of a gas because that's what we breathe in, and hydrogen's in the atmosphere. But at its solid state, hydrogen has metallic properties, which is kind of bizarre, but we just don't ever see it get that cold. All right, here we have aluminum and oxygen. And here we have a metal with a non-metal. Aluminum has a 3+ charge. Oxygen has a 2- charge. What number will they meet at? 6, okay. How do I get to 6? 2 aluminum total and 3 oxygen total, okay? Because now I've got 6 charge on my left and 6- charge on my right. They cancel each other out. So what compound did they form together? It'd be 2 aluminum and 3 oxygen. So this is Al2O3. And notice all I'm focused on right now is getting the product. I do not much care about us balancing right now, okay? I know that we could do that. We've done a section on balancing. But right now I'm just focused on can we get a product? All right, so that's synthesis. You're given 2, and I'm only going to give you 2 reactants. You got to find out what's the product going to be that they form together. With decomposition, we're doing the exact opposite. And for decomp, what we need to remember is Hofbrinkel, okay? So these elements cannot exist alone as a product or a reactant, okay? So NaCl, if we have 1 reactant and it's going to go to 2 products, well, it's pretty easy to figure out what products those are going to be because we just have 2 elements. We have sodium and we have chlorine. So yeah, we're going to have sodium. Yeah, we're going to have chlorine. The question is, which of these can exist alone, which can't? Can sodium exist alone? Yes, because it's a metal. Okay, ooh, that's weird. Sodium can exist alone because it's a metal. So sodium can exist alone. Chlorine cannot because it's a part of this Hofbrinkel group up here. Chlorine is not stable enough to exist alone. Therefore, chlorine always, if it's alone as a product or a reactant, is going to have a formula of Cl2. It's diatomic, as we say. All right. Similar thing down here. What we got is we got aluminum, a metal, and bromine, a non-metal. So we have aluminum and bromine as our products. The question is, can they exist alone? Aluminum is a metal. It can exist alone. Bromine is not a metal. It's one of the ones that are part of Hofbrinkel, so it's going to be Br2. Okay, so that's just what we have to watch out for with these is, okay, of my products, can they exist alone and then change it accordingly? Fe2O3, we're starting to see a pattern. You have a metal, and then you have a non-metal, and typically that non-metal is going to be diatomic. So like oxygen here is going to exist as O2. This is the opposite of rust. You have rust going to iron and oxygen as opposed to the opposite. NH3. This is the first one we're seeing here where it's 2 nonmetals. So this is going to break into nitrogen and hydrogen. So of these 2, okay, which one's a metal? Neither of them. Therefore, we go back up here. Okay, hydrogen has to be diatomic, and so is nitrogen. So they both form diatomic products. So NH3, ammonia, produces nitrogen gas and hydrogen gas. And then lastly, from these, we have water. Water is going to split into hydrogen and oxygen. Same exact thing. Hydrogen's a part of Hofbrinkel. Oxygen's a part of Hofbrinkel. So the only ones that we notice from this that exist alone are going to be our metals. Sodium, aluminum, iron. A metal can exist alone. All these other nonmetals are almost always diatomic. Hofbrinkel, they got to exist in pairs. So decomp, you're going from one compound to multiple, usually 2 products. Okay. This is introducing the activity series. So now when we do single displacement, we got one element wanting to kick another out of the compound. Well, we got to figure out if that element is strong enough to kick an element out of the compound. So we have a pecking order, and this is the pecking order as such. So on the left, we have our strongest elements. Okay, these guys can, lithium can displace any other one from a compound. Lithium is the strongest. All the way down to we have gold. Gold is super, super weak when it comes to displacing an element from a compound. It doesn't do it well at all. Same thing with these guys down here. These are just our nonmetals. So we have strong, which is fluorine, and weak. Okay. So it's called activity. So lithium is our most active element as opposed to gold, which is our less active element. And what we're saying is, if we want to know, can magnesium kick zinc out of a compound? Well, magnesium is on the stronger end of the pecking order than zinc is. So magnesium could kick zinc out. But copper cannot kick nickel out. Yes, I've got paper copies for you. Absolutely. You can pick them up. Copper cannot kick nickel out because copper's weaker. It's toward the weaker end of the spectrum than nickel. So it cannot kick nickel out. There's going to be no reaction. So basically, if you have two elements in question, whichever one is trying to displace the other, you got to look to see if it's farther left or farther right. An element can replace any other element to the right of it. Okay, lithium can replace anything to any of these elements. Copper can only replace silver, mercury, platinum, and gold, but it can't replace anything to its left. So what does that look like? Okay, well, if we're looking at potassium wants to displace sodium from sodium chloride, we ask ourselves, okay, will that work? So what we do is we find sodium from this pecking order, potassium from this pecking order, and sodium, and we say, okay, based on where they're at, can sodium kick out, or can potassium kick out sodium? And the answer is yes, okay, because it's on the left side. It's to the left of sodium in the pecking order, it's stronger. So what we're going to see is that potassium is going to kick out sodium. And so it takes its place, and then sodium is now the loner. So it's just this kicking out, and then now we have another loner that's different. But this doesn't always happen. So for example, with zinc is trying to displace calcium. So if zinc is trying to displace calcium, then we find them both in the chart. There's zinc and there's calcium. But calcium is to the left of zinc, which means it's stronger. So zinc tries to kick out calcium, but it can't. Therefore, we have no reaction. So what does this look like in a lab sense? Well, if we had potassium and we dropped it in salt water or sodium chloride water solution, we're going to get a reaction that takes place. We're going to notice a reaction. If we dropped zinc metal into calcium bromide solution, we're going to get no reaction out. So this series tells us if we're going to get a reaction based on mixing a metal with a certain solution. So let's do some examples. We have chlorine here, and we have sodium bromide. We want to know, can chlorine kick out? Well, which one is going to try to kick out? It's going to want to kick out the nonmetal because chlorine is a nonmetal. If it's whatever the loner is, it's going to kick out something that's like it. A nonmetal will never kick out a metal and vice versa. So chlorine is going to want to kick out the other nonmetal here. So what we do is we look at our chart. Chlorine's right here. And we want to know, can it kick out bromine? Can it? Yes. Okay, because it's further left. So it's got a higher activity, so it can kick out bromine. So what does that look like? Well, if chlorine can kick out bromine, actually, let me redraw that. If chlorine can kick out bromine, then that means chlorine's now with sodium. So we have sodium chloride, and bromine's our loner. So bromine's now the loner. Question is, am I done? Answer is no. So I got to check to make sure my products make sense. Are these formulas correct? Well, bromine, can it exist alone? No, it can't. It's part of Hop-Wrinkle. So bromine's up there. It exists in pairs. So we're going to get Br2 out instead of Br. What about sodium chloride? Is this correct? Is it NaCl, NaCl2, Na2CO? Well, Na has a +1 charge. Chlorine's got a 1- charge. Therefore, yes, it's a 1-to-1 ratio. We're good here. Here we have zinc and copper. We want to know, can zinc displace copper from copper chloride? Well, zinc right here, copper right here. We don't know, can zinc kick out copper from the solution? Well, zinc is way further left than copper, so absolutely it can. So what we're going to get is we're going to get zinc taking copper's place. So we have zinc chloride, and we have pure copper coming out. Question is, do my formulas make sense? So we have pure copper. Should it be Cu2? No, because copper can exist alone. It's not like bromine, which is a part of Hofbrinkel, and these guys always exist in pairs. But copper is a metal. It can exist alone, and it's fine to do that. All right, what about zinc chloride? Well, this one, you don't really know the charge of zinc. Zinc is going to be +2. We didn't really talk about that. I think it's on your resource sheet that I gave you that zinc is usually always +2. But I wouldn't give this one on a test or quiz, but this is correct. All right, let me clean this up a bit. Plus Br2. So we have magnesium, and we got hydrochloric acid, so HCl. This one's unique because we have magnesium, which is a metal, and then neither of these are metals. Hydrogen's not a metal, chlorine's not a metal. So what do we do? Well, kind of weird, but hydrogen is included on this metal chart. Why is that? Because hydrogen, in some weird ways, is technically a metal, okay? So a lot of times we associate it with metals, and it can be in an ionic compound. So hydrogen here, we're going to consider a metal. Magnesium actually wants to displace hydrogen from hydrochloric acid, or HCl. So there's hydrogen. So where's our magnesium at? Magnesium is up here. So can magnesium kick out hydrogen? The answer is yes. Magnesium can kick out hydrogen. So what are we left with? We're going to have MgCl, and hydrogen is the one that got kicked out. So are my products right? Well, hydrogen, can it exist alone? No, it's a part of Hofbrinkel. So it's going to be H2. MgCl, is this the right formula? Well, magnesium has a 2+ charge from our periodic table. Chlorine's got a 1- charge. So is that the right formula?
No, you need to put a 2 after Cl.
Very good. You need MgCl too. Okay, so now we're done with that one. All right. And now we have copper. And we want to know, can it displace aluminum? Copper is a metal. Can it displace aluminum from aluminum chloride? So we have aluminum right there, and we have copper right there. What are my products going to be? What are my products going to be? Jack, you know. It's going to be the exact same thing. There's no products. There's no reaction here. Why? Because copper is to the right of aluminum. It's weaker. This is a pecking order. Copper is weaker, so it's too weak to kick out aluminum, which is stronger. So this is going to be no reaction. I abbreviate reaction with RXN. You'll see that in chem textbooks too. Reaction, okay? My chem teacher did it. I didn't really know what it meant until like halfway through AP Chem. I had no idea what she was writing. RXN is reaction. So you don't write the products again because no reaction took place. You just put no reaction. And that's totally fine. All right, so that's single replacement. And then here's double replacement. So I don't think we got to this yesterday. If we did, we didn't do too much with it. Double replacement, remember, is switching partners. So it's like you go to prom with your buddy and his date, and you got your date yourself, and then you just switch partners. Okay, kind of weird, but this is what double replacement is. So, scenario: we're given copper chloride and H2S gas. All right. What happens when you switch partners is the cation ions are going to switch, and they're going to have new partners. So copper is going to switch with hydrogen, and they're going to form new compounds. So instead of copper being with chlorine, we have copper now with sulfur. So we have CuS, and what's our other one? Well, now we have hydrogen with chlorine, HCl. So that was our switch. Now we got to check to make sure that these compounds make sense. Well, here we see we have 2 chlorine. Each chlorine has a 1- charge. So therefore, what charge must copper have? 2+. Very good. Okay. Over here, we have sulfur. Sulfur has a 2- charge, but we have it bonded to 2 hydrogen. So what charge must hydrogen have? 1+. Okay. So now we go over here. We got to make sure that we have the right products. So copper had a 2+ charge. Sulfur had a 2- charge. Is that right? Yes. Okay. It's 1-to-1 ratio. Over here, we have hydrogen and we have chlorine. Hydrogen's got a 1+ charge. Chlorine's got a 1- charge. Are we good there? Yes. It's a 1-to-1 ratio. Okay. So I don't need to add a 2 down here. I don't need to add a 3. We're all good as it was written the first time. Here we got sodium chloride and silver nitrate. Sodium and silver are going to swap places. Just like that. And now sodium is going to be with nitrate, which is NO3. And silver is going to be with chlorine, AgCl. Well, what are my charges? What were my charges? Well, sodium has a 1+ charge. Chlorine's got a 1- charge. That's easy. Silver, we don't know. Silver's a transition metal. But nitrate, that is a polyatomic ion. So from the resource sheet, you can see, okay, nitrate's got a 1- charge. So if we have 1 silver bonded to that, what charge must silver have? 1+. Okay. So sodium's got a 1+ charge. Nitrate's got a 1- charge. Are we good? Yes. Over here, silver's got a 1+ charge. Chlorine's got a 1- charge. Are we good? Yes. So we are all good there. Nothing we had to change again. And then this one, a little bit more confusing. We have potassium, we have iodine, we have lead, which is Pb, and we have nitrate. Potassium and lead want to switch. Okay. Well, let's do the charges first. Potassium's got a 1+ charge. Iodine's got a 1- charge. Lead, we don't know. Nitrate's got a 1- charge. If we have 2 nitrates bonded to lead, what charge must lead have? We have 2 bonded to it, +2. Okay. So when we have 2 nitrates, 2 of these polyatomic ions bonded to lead, then it's going to be +2 charge. All right, so let's swap our partners. Potassium is now with nitrate, and lead is now with iodide. So let's make sure that we know what we're doing. Potassium's 1+ charge, nitrate's 1-. Are we good there? What? Yes, you're right. So we're good here with potassium and nitrate. Over here with lead and iodine, okay, lead's got a 2+ charge, iodine's got a 1- charge. You're going to need 2 iodide. Okay. One more, then we're done. Okay. You're like, finally. Here we got sodium and we got hydrogen. They want to swap places. So sodium's got a 1+ charge. Hydroxide is an ion, a polyatomic ion. It's got a 1- charge. Chlorine's got a 1- charge. Therefore, hydrogen must have a 1+ charge. So what's it going to form? Sodium is now with chlorine, and hydrogen's now with hydroxide. So sodium's got a +1 charge. Chlorine's got a -1 charge. They're good. Okay, nothing to change there. Here we have hydrogen with a 1+ charge. We have OH with a 1- charge. They're good too. But what is HOH? That's just water. HOH is H2O, which is water. So really, this reaction just made salt and water. Okay. So that's double replacement. What you're doing there is you're swapping partners, asking yourself, do I need to change the formula all based on their charges? Okay. That's that.